So for the next 2 days, we are going to be solving equations. You know, if you think about algebra, algebra really only has a couple of different instructions. Simplify and solve are the two main instructions you run into in algebra. And solving equations is a matter of taking an equation you haven't solved before and turning it into one you know how to solve. So here's how it goes. The equations you're given today are going to contain a logarithm or 2 or 3. And it'll be your job to get rid of those logarithms somehow. The equations you get tomorrow won't have logarithms in them. There will be exponential functions, and then we'll be solving using a logarithm. So today we're going to get rid of logarithms. Tomorrow we're going to bring them in. All right, a bunch of things to recall. E to the x and natural log of x are inverse functions. In fact, a to the x and log base a of x are inverse functions. So if I want to get rid of a logarithm, I will bring in its inverse. Just like if I want to get rid of a square root, I will square things because that square is the inverse of the square root. A raised to the log base a of x is x. All we have here are inverse operations. This is what we're going to be doing today. We're going to see a logarithm. I need to get rid of that logarithm. I will insert base a to get rid of it. E raised to the natural log of x turns out to be x. This is just a specific example of this rule. This a means it's true for any base. When I use natural log, that means the base is 2.71828. It's true for any number. Obviously, it's true for 2.71828. Log base a of a to the x turns out to be x. And natural log of e to the x turns out to be x. There's a couple of different ways you can think about this. What is the natural log of e? 1. So if I think of it like this, this is x times the natural log of e when I pull the exponent down. Turns out to be 1. At the same time, I can pull this x out, and it's x times log base a of a, which is also 1. All right, so the natural log of e is 1. And the natural log of 1 is 0. If you don't know what to do, feel free to change the base. I highly recommend changing to the natural log base, but you can change to log base 10 if you'd rather. You can change, yep. Okay, now, most of the time when you're dealing with logarithms, you get irrational numbers for your answers. Not always. I mean, you had some answers yesterday that were 3 and 6, but usually you're going to get strange-looking numbers. And we're just going to leave them in exact form. We're not going to convert natural log 2 to 0.693, I think it is. We're just going to leave it as natural log 2. So we will want exact solutions instead of decimal approximations. Golden rule of math is you can do anything you want to an equation as long as you do the same thing to both sides of the equation. When you do something to a side of an equation, that doesn't necessarily mean you do it to each term in an equation. Okay, so here, let me show you an example of that. I think we can agree that 3 plus 4 is equal to 7. I can take the left side of this equation, insert a base of 2. As long as I insert a base of 2 on the right side of the equation, I've done a legal maneuver. Those are still equal. But a lot of people are going to go to here, and they're going to say, all right, 2 to the 3 plus 4 is 2 to the 3rd plus 2 to the 4th. In other words, they're going to distribute this 2 to the individual terms and still want that to be equal to 2 to the 7th. But the bottom line is 8 plus 16 isn't actually equal to 128. So if you see this 3 plus 4 is 7, and you say, all right, I'm going to insert a base of 2. I can do it to the side of the equation. That's different than putting it with the individual terms on the side of the equation. Big mistake. That hopefully doesn't occur to you. It doesn't happen to you. We can always convert logarithms to exponential form. Log base 10 of 100 is 2 is the same as 10 squared. How would you solve this equation, Ryan?
Put 4 in the second.
Insert a base of 4 on the left, insert a base of 4 on the right. Those will be gone, and we'll have x equals 4 to the 3rd power. There's nothing more to it than that. How would we solve this equation? Yes, Carter.
Why can a log not have a negative base?
Why can a log not have a negative base? Because the person who either invented or discovered them said so. Seriously.
Kind of like the square root deal.
If you gave a logarithm a negative base, you get all kinds of weird things to happen. I'll show you. Log base 10 of x. Okay, that does this. It goes through 1, 0. It goes through 10, 1, right? And log base 10 of 100 is 2 because 10 squared equals 100. Now, if I decided I'm going to try to do a logarithm with a negative base, log base negative 10 of x. Let's see how that works out. Let's say I put a positive number in here, like 100. I could take negative 10 to the x power, and that's got to equal 100. I think I can make that work. X would be 2, correct? Can I take... I'm trying to think what the weird things that would happen are. I've looked at it before, and it's not occurring to me right now. But the bottom line is, whoever invented or discovered logarithms, and that would most likely be a guy named Napier, he figured out there would be some very negative ramifications to allowing that, and so he just said, we're not going to do that. I have to think about it a little more to see if I can spot what they are. All right, back on topic. How are we going to solve natural log of 3x plus 5 is equal to 8? Insert a base of e. That gives me 3x plus 5 is equal to e to the 8th. Now what? And finally, now this is what I was saying a minute ago. You're going to have some strange looking answers. Just leave it as a strange looking answer. There's no need for you to punch that into your calculator and find out that it's whatever number it is rounded to the nearest thousand. Just get used to having abstract looking values on an answer. Let's skip that. So here's what it's really all about. If you want to solve an equation that has a logarithm in it, isolate the logarithm term. Get that alone first. Then bring your base a in. You can use any base you want, but usually there's a pretty convenient choice to work with. And then once you get done with this adding of the base, you'll be back to an algebra 1 problem in most instances. Finish the job. But isolating the log term is going to be key. And then you have to compress your problem so that you can have at most one logarithm on each side. And I'll show you the hardest of the problems are where you have more than one logarithm on a single side of the equation. We can fix that based on the things we learned yesterday or practiced yesterday. It's just something you have to get used to all over again. Okay, so if I want to solve this equation, the log term is isolated. I'm ready to bring in my base. Insert a base of 3. There's no logarithm in there anymore, and what do I have? 5x minus 1 is equal to 3. I've got an algebra 1 problem. Once you get rid of the logarithm, it should be smooth sailing from there. What's the first thing you would do here, Ben?
Subtract 5.
How come?
Get the log alone.
Yeah, we want to isolate that logarithm. So I would definitely subtract the 5 first. And then what?
Base b.
Yeah,
5 and
2. We want to isolate that logarithm. Now, there was an alternative. You could have actually put that 2 back up as an exponent. But when you do that, you may create an extra solution. So we'll be on the lookout for that. I'll show you an example of that in just a minute. Work with that. Okay, so here's the more challenging thing. I've got two logarithms on the left. That's not a situation where I can insert a base of 2, because as I showed you earlier, I can't just put the 2 on the individual terms. I can put a 2 over here and apply it to the whole thing, but I can't put it in each spot. So what I'm going to do is take this and rewrite it as one logarithm. Log base 2, subtraction between logarithms is the same as equation within 2x plus 1 over x minus 3 equals log base 2. Again, I'd like to isolate the logarithm. This 2 is a headache for me, so let's slide it back up there and call this 3 squared, or 9. Now that I've got at most a single logarithm on each side, those are going to go away quite easily. 2x plus 1 over x minus 3 is going to equal 9. What do I have again? Algebra 1. Okay, so the last thing we have to look at here is the concept of solutions that don't work. I want to insert a base of e, but we've got two logs here. Happily, addition between logarithms is the same as multiplication within. So I can quickly compress this. X minus 2 times 2x minus 3 equals the natural log of x squared. I'm going to move that back up as an exponent if I have to. If I could divide it out, I would. And then I insert a base of e, and I'm left with x minus 2 times 2x minus 3 is equal to x squared. That's algebra 1, but let's be careful. 2x squared minus 3x minus 4x plus 6 is 0 gives me, wait, it's not 0, is squared. Move that over, I get x squared minus 7x plus 6 is equal to 0. Again, I still think we're working on algebra 1. X minus 6 and minus 1. So how about x equals 6 or x equals 1? Not bad at all. Except one of those two answers is wrong. What's wrong with the 1? If I put a 1 in here, okay. If I put a 1 in here, I'll have a negative inside of a logarithm. This one is no good for me. Now, when does that potentially happen? When you compress. And most specifically, where you might run into that issue is if you move an exponent back up. But just the simple act of taking those two and making them 1 means that you might end up with a number that doesn't work. Because I could have a negative here and a negative here, and when I combine them, those two negatives give me something that's positive inside the logarithm. So I have to be aware of that. If you do this compression, make sure you check your answers. 6 minus 2 is positive, 12 minus 3 is positive, and 6 is positive. That one works. Plugging this 1 into here gives me a negative on the inside of a logarithm. Here's another negative inside a logarithm. That one is not allowed. And that is all I have to say. Give that a try for tomorrow.